Homework is due tomorrow. All right, your first homework assignment, so it's the one that's marked due August 28th. We had a hurricane. Okay, so it's due tomorrow.
Excuse me, Miss Kennedy. The homework is due tomorrow at midnight or before classes start?
At midnight.
Midnight. Okay.
As long as your email says it was sent before midnight. So by the time September 4th ends, it's got to be in for it to count.
Okay. Thank you so much.
You're welcome. And remember, you need to submit it as one PDF file. And it needs to be readable. Okay. That's very important. It's hard to grade something you can't see. And send it to Mr. Miller. Okay. His email address, well, it's listed on the item called homework submission. I got it here somewhere. Mr. Miller, what's your email address? You're right here.
It's AM, I think it's 761624 @gmail.com.
Okay, got that. And the other one is our class email, so that will go to me. So JK Calc2413 JK Calc2413 at yahoo.com. So yes, has to be submitted in a certain form, needs to go to our class email address and to Mr. Miller. Mr. Miller is going to be the one who grades your homework, and I'm very grateful for that. Okay, so let's see. Okay, I'm still working on the co-host thing, huh?
Could you say your email one more time, Ms. Miller?
Tell you what, well, okay. Just as soon as I switch over to sharing the screen, I'll write it down. All right, if you'll remind me. I moved the exam from Friday, September 11th to Friday, September 18th. You'll get a new homework assignment, which I should post sometime this afternoon, that will be due on September the 11th. So, okay. And I think that's all I wanted to say this morning. Any questions before we get started with our actual math?
Well, ma'am, I was kind of speaking about how that homework is due tomorrow. If we had already submitted it before last Friday, would it be okay to go back and if we may have not been particularly happy with some of our answers, would it be okay for us to go back, check over our walk, and resubmit it?
Yes. Yes, you can resubmit if you want. We will grade the most recent one submitted. Okay. Okay, so let's go to math, the shared screen. Okay, and okay, 2413. All right. Okay,
Before we begin, just a heads up, my internet connection is saying it's unstable at the moment. So if I drop out, that's probably why.
okay, yeah. Always going to be technical problems, I'm afraid. Mr. Miller, say your email address again, please.
Oh, I can type it up in the chat.
Okay, that's better.
Yeah.
And would you put the one for the class in there too?
But
Okay, well, I know that one. Let's see. Okay, so Mr. Miller is going to do the chat, going to put his email address in the chat. And okay. This is our class. And okay, all this information's on Blackboard. Okay, it's there for you. Very long list of things. So if you have questions, go to the homework submission. There's an item that's called that, I believe, homework submission. It's got all the details. Okay, so we were talking about yesterday. We defined the velocity for a function. So you start with the function defined on an, okay, actually needs to be an open interval containing a, then the velocity at a, well, it's really a new function. The velocity at a, oops, left out the a there, is the limit as x approaches a of f of x minus f of a over x minus a. And v at a is the velocity. We say velocity, or if you really want to be careful, instantaneous velocity at a. And okay, we did an example or two yesterday. Let's do another one today. What's the velocity of f at a when a is greater than 0? And our function is f of x is equal to the square root of x, which has a domain 0 to infinity. Okay, so it wouldn't make any sense for me to ask what the velocity of f is at, say, -1. -1 is not in the domain. Okay, so we want to compute this limit, assuming it exists. Yeah, and sometimes functions don't have this limit, so you can't talk about the velocity at a point if the limit doesn't exist. Okay, but this one's going to. So for this particular function, this is the limit as x approaches a of the square root of x minus the square root of a over x minus a. And notice now, if I tried plugging in a right now, I would get 0 over 0, which is meaningless. In fact, anytime you get that form, because 0 over 0 is not a number, that means that you have work to do. It means you don't know, okay? You got to do some more work to find out. Okay, but we can do work here. And I've got the difference of two square roots there on top. I'm going to use this little trick of rationalizing. So I'm down to the problem of just evaluating a certain limit. I can use the kind of tricks we did before with evaluating limits. Okay, so the conjugate of square root of x minus the square root of a is the square root of x plus the square root of a. And okay, so now notice I haven't changed the problem at all, because this is really just 1. It's something divided by itself, so it's just 1. I have not changed the problem. I've just written it in a different way. Well, the nice thing about using this conjugate is that the square root's going to go away in the numerator, because if you have let's see. If you have x minus y times x plus y, there's no middle term. Basically, it adds out. It's minus xy and plus xy. Okay, somebody just came into the waiting room. Mr. Miller, I really want to figure out a way to make you co-host, but I don't see it yet. Okay, back to the shared screen. Okay, so I'm going to use this little fact to eliminate the square root in the numerator at least. It's going to give me square root of x times square root of x is just x, and square root of a times square root of a is just a. But then I still have the square root of x plus square root of a in the denominator. Okay. But look what happened. Now I've got, oops, color changed. X minus a on the top and x minus a times something on the bottom. I can cancel. Maybe I will use blue for that. Okay. Can cancel those out. And really, when I did that, I got rid of my 0 over 0 problem. Now I'm down to taking the limit as x approaches a of 1 over the square root of x plus the square root of a. And now I can just use direct substitution and put in a for x. So that's 1 over 2 times the square root of a. Any questions?
No, man.
Okay, thank you for answering. Okay, I'm going to consider another problem. Yeah, so we have this special limit that gives us the velocity of a function at a point. It turns out that this problem is strongly related to that. All right. So, well, I'm taking a specific function. F of x is equal to x squared, so a parabola, simple parabola. And I've got it sketched right there, the black. What is the slope of the tangent line to F at the point 1, 1? Okay, so tangent line, I want it to touch the graph, so that the red is a picture of the tangent line. I want it to touch the graph. Oh. There, only at the point 1, 1. Okay, that's what you call the tangent line. How do I figure out what that slope is? Well, let me kind of blow it up here. Got this curve, and here's my point 1, 1. What I'm going to do is take a point close to 1, 1. So this would have coordinates. In fact, let's call it x. This would be x squared. So a point pretty close to 1, 1. And draw the what's called a secant line through those 2 points. Okay, this is just a rough sketch, but okay, that secant should be pretty close to being the tangent line. Okay, It's not the tangent line, but it should be close to the tangent line in some sense. And in fact, the closer I take x, I'll call this one x prime squared. The closer I take that point to the point 1, 1, the closer that secant line that I get that goes through 2 points on the curve is going to get to the tangent line. And okay, what's the slope? The slope of a line, and tangent lines are lines, but just in general, the slope of a line is rise over run. Whoops, not rum. Jeez. Okay, so if I look at the secant line, that contains points x squared and 1, 1. So I've got curve, I have 2 points, and I want the slope of that line. Well, if you got 2 points in the plane, it determines a line, and the slope of the line, we all know, is, okay, rise is the difference in the y coordinates. So x squared minus 1, and then run is the difference in the x coordinates. So x and 1. That's the slope, okay? And if I take a point closer to 1, 1, the secant line gets closer to the tangent line, which I can kind of sketch right there. The red thing is a tangent line. The closer the point is to 1, the closer the secant line is to the tangent line, and the secant lines have slopes that look like that. Okay, so again, I'm taking a limit. I'm taking a limit of the slopes of the secant lines. As x approaches 1. All right, so that is, so then it's reasonable to think that the slope of the tangent line is that limit of slopes of secant lines. So the slope, I'll call it m, of the tangent line to y equal to x squared at the point 1, 1 is given by the limit, okay, m equal to the limit as x approaches a of x squared minus, oh, a is 1 here. X approaches 1. Okay, so x squared minus 1 over x minus 1. And okay, this is up here. I call that M2. M just means slope. This is the slope of a secant line. So one that goes through 2 points. But by taking the limit of the slopes of the secant lines, which is what this, all of these for every x, each x here gives when you stick it in this expression, okay, gives the slope of a secant line. And by taking advantage of the fact that the secant lines are getting closer and closer to the tangent line, and the slopes of the secant lines are getting closer and closer to the slope of the tangent line, I can take the limit and get the slope of the tangent line. And when I say each x gives the slope of a secant line, I mean that when you stick it in this expression right here, okay, that is the slope of a secant line. Okay, so again, it's a special limit. It's got the same form as that velocity function did. So let's compute it. Finish the problem. So M is the limit as x approaches 1, x squared minus 1, because 1 squared is 1. And this one's pretty easy. Well, you can't substitute in 1 because you get 0 over 0. That's meaningless. But I can factor the x squared minus 1. Okay. And that gives us then x minus 1 times x plus 1 in the numerator. The x minus 1s will factor out. And then we can just use direct substitution to get the limit, and it's 2. In fact, this little procedure works in general. Yeah, well, I pretty much used up all my room, but at least I didn't run out of it. Okay, so in general, if you have a function defined on an open interval that contains a, the slope m, the slope m of the tangent line at a of f is given by this limit. M is the limit as x approaches a of f of x minus f of a over x minus a. Well, that's the same thing as the velocity at a. Exact same limit. So m is velocity at a. And in fact, m is also a function of a. Okay, so it's the slope of the tangent line generally changes as you change the point. So it really ought to be m of a. But they're the same limit. In fact, this limit has many, many interpretations and many applications. And what it's measuring is rate of change of the function as you're going through A. It's the rate of change. Anytime you see rate of change, this limit is what you're talking about. And yeah, it's a rate of change of f at a, and we're going to define then the derivative of f at a. Okay, because not only can this limit be a velocity function for f, or give the velocity to a point, and not only does it give the slope of the tangent line at a point, or a formula for the slope of the tangent line at all the points. It gives many things. You can use it in many, many ways. So we're going to define the derivative of f at a to be this limit. The limit as x approaches a of f of x minus f of a over x minus a. Okay. So f prime of a is slope m of the tangent line of a is equal to the velocity at a. They're all the same thing. And we're going to call them derivatives. Okay, so let's see. Let's do some. So now we're computing limits, but it's a special kind of limit. It's not just the limit as x approaches a of f. It is, okay, so for f of x, do f prime of x. Okay, so for f of x equal to x squared plus 1, well, I'm going to get the derivative in general. So suppose that this function is defined for all reals. So that means I can find the derivative at any point. So suppose a is a real number. Now use this blackboard bold, that means the reals. Okay. Suppose a is a real number, then f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. And that's equal to the limit as x approaches a. Okay, so now put my function in. So x squared plus 1 minus a squared plus 1 over x minus a. I can add the ones out. So that goes out, 1 minus 1. And that gets me to a little bit simpler expression. X squared minus a squared over x minus a. So looks a lot like the last problem we worked, except in there a was 1. But same deal, same thing works. Factor the top. And now you can cancel out the x minus a's. Okay, because they're multiplied in the top and the bottom. And once you do that, you're done with your 0 over 0 problem. It's gone away. So we're just down to computing the limit as x approaches a of x plus a, and that's just a plus a. So I substituted in a for x. Once you do that, the limit sign goes away, okay, because you have evaluated it. So you get 2a. So we got a formula for f prime at a is 2a for each a in the reals. And if you want to call a x, the reason I didn't call a x up here is because, okay, right now when I'm computing the derivative at A is fixed. But X is not. X is a number that's not equal to A, but close to it. And I can't have the same letter in both those slots. It wouldn't make any sense. So I have to use 2 letters. But the formula, actually, I've got a formula for the derivative of F at A now for each number A out of this. And let's see, let me kind of draw a picture. X squared plus 1 is not too hard to draw. In fact, it's just that parabola we had before. Whoops. But raised up 1. Okay, just very rough here. Looks something like that. So let's see, when A is 0, let's draw some tangent lines. When A is 0, the tangent line ought to be horizontal, right? So it should have slope 0. Well, f prime of 0 is 2 times 0 is 0. That looks plausible. At the point, let's see, if I put in 1, what point on the graph? This is a rough sketch, so in my graph, it looks like if that point is 1 f of 1, which would be equal to 2. May as well put the 1, 2. The slope, okay, that's the point on the graph that's has x coordinate 1. The slope of the tangent line there would be 2 times 1 is 2. Okay, so positive slope. And that seems kind of reasonable. It's hard to tell with my very, very rough sketch, but it certainly seems plausible. F prime at minus 1 would be minus 2. Okay, and minus 1, let's see, call it that minus 1. That would be the point minus 1, 2. But it has negative slope, and that makes sense over here. The tangent line is going to be pointing down. Okay. So what we've got here is a formula for the slopes of the tangent lines. When you change your A, you change the tangent line, you change the slope of the tangent line. Any questions?
No, man, I think we're good.
Okay, well, let's do the second one. That's the radical again. And that's going to work out very similarly to what square root of x did. Okay, so what's the domain of that function? Square root of x plus 1.
It would be all real numbers or all real positive numbers.
All real positive numbers. In fact, you can actually take it from minus 1 to, minus 1 and up, right? Because minus 1 would give you 0 under the, okay. Minus 1 plus 1 is 0, square root of 0, 0. Yeah, so it does contain all the positive numbers, but it actually goes a little bit further. Okay, so it makes sense to talk about, in fact, I could draw it. Let's see. It's going to look like that, more or less. Okay, we want the derivative. So we're computing the special limit. So f prime, again, I need another letter if I'm going to let x be the one that changes, that goes toward A. this is the limit as x approaches a of f of x minus f of a over x minus a. And that's the limit as x approaches a of the square root of x plus 1 minus the square root of a plus 1 over x minus a. Okay, so I've got two square roots, and I'm going to use that rationalize idea again. That little trick works with sums and differences of square roots and not much else. Okay, so let's see. So I'm multiplying by 1, basically. I'm not allowed to change the problem. I am allowed to write the problem in a different way as long as it's not really changed. Okay, so this whole thing is just equal to 1. So I haven't changed anything, but it's going to allow me to get rid of that square root in the numerator. It does not go away in the denominator, but it's not really a problem in the denominator, as we shall see here. Okay, so square root of x times square root of x is just x plus 1. And then middle term goes out. Again, we're using this c plus d times c minus d. That's c squared minus d squared. Oh, yeah. The whole point of that, the changing the minus to a plus is to make the middle term go away. Legally, didn't just throw it away. Okay, and then square root of a plus 1 times square root of a plus 1 is a plus 1. And I've got x minus a in the denominator, and I've still got the square root in the denominator, square roots. But, okay, now, well, the ones add out in the numerator. So, got x minus a. On the top then. And now, I've got a factor of x minus a in the top and a factor of x minus a in the bottom. So I can cancel. And once I do that canceling, the 0 over 0 problem is gone. And I can just use direct substitution. Okay. Replace x with a. And that just gives me 1 over 2 times the square root of a plus 1. So for this function, or if I replace a by x now, okay, when I write this, then this x is not approaching a anymore. Okay, that's, we dealt with that. We're finished with that. F prime of x is that. So again, you get a formula for the slopes of the tangent lines. Also the derivative, also the velocity. Okay. And I'm trying to remember what the problem next one. Okay, 1 over x plus 4. Any questions about that one?
Excuse me, Jasmine, I have a question.
Okay.
Where did the x plus 1 go? I mean, can you go back a little bit?
Yeah, just let me write this problem
Okay,
down.
yes, no problem, no
Before I
problem.
forget. Okay. Where did you mean right here?
Yes, right there.
Okay, well, I've got,
I get a little bit lost there.
okay, so what I've got up there, just in the numerator, is x plus 1 minus a plus 1. But the a plus 1 is in parentheses, so the minus
yeah.
a, yeah, so it's minus a minus 1.
Okay, I got it. Okay, thank you.
You're welcome.
Okay.
Okay. Any other questions before I go to the last? Maybe I'll leave the last example. Okay, let's work one more then of these, and then I'll tell you a little bit more. Okay, well, this one, okay, what's the domain of this one?
Would it be all numbers except for -4?
Yes, all reals except x equal to -4. Okay, in fact, you've got a vertical asymptote at -4 for this function. Okay, so we want the derivative. Oops, let's not call it x unless I want to let the stuff that approaches be called something else. So let's call it a. Okay, and that goes back. All right. F prime of a is the limit as x approaches a of f of x minus f of a over x minus a, and that's the limit as x approaches a of 1 over x plus 4 minus 1 over a plus 4 over x minus a. Okay, so we have a difference of two fractions in the numerator. Usually when this happens, I'm going to go with finding a common denominator to start with for those two fractions in the numerator. Okay, so this would be, well, the common denominator, common denominator, and now that stupid line appeared. I have no idea why. Well, let me just get down below it because it won't let me write on it. Okay, so this is and it's not writing. Oh, there it is. This is the limit. Yeah, it helps to have the pencil on. As x approaches a of big line over x minus a, but then the common denominator in the numerator is a x plus 4 times a plus 4. So the numerator now becomes a plus 4. Okay, why are you messing up on me? Okay, sorry. This iPad has its personality of its own. Okay, this is, and now that changed. Okay, let's go with red. This is a plus 4 minus, oh, was it minus? Yeah, it was minus. Okay, minus x plus 4 there. Okay, and notice if okay, I can't do that. You can't see my pencil. But if I block out the x plus 4, then the first term is the a plus 4 is canceled, so it's 1 over x plus 4. If I block out the a plus 4 in the numerator, then I've got minus 1 over a plus 4. So that is the same thing. This is the same thing as this. Okay, I just changed the form by getting the common denominator. And this is equal to, the limit is x approaches a. And okay, so, and again, now in the numerator, I've got a plus 4 minus x plus 4. That minus applies to that 4. Okay. Oh well, yeah, to the second 4. So again, the red numerator. So the numerator of the numerator, the 4s add out, and now I'm gonna have just, oh dear, okay. I'll just erase that first. Now I'm gonna have a minus x over x plus 4 times a plus 4. Okay, 4 is added out. Okay, now we have a complex fraction. And I can use the rule, this is really x minus a over 1. When you have a over b all over c over d, it's equal to ad over bc. So I can use this to change the form of what's inside my limit. And this is the limit then as x approaches a of a minus x times 1, d is 1, and then x plus 4 times a plus 4 times x minus a. Okay, well, a minus x and x minus a, they look sort of similar, but I can do this. I can factor a minus 1 from the numerator. So minus a minus, yeah, if I pull the minus out, that's going to be x minus a, minus the quantity x minus a, okay? Because you apply the minus, put another side note here, minus x minus a is, okay, minus x minus a is minus x plus a. So this and this are the same thing. And I still need to write the denominator. Okay, but now I have x minus a on the top and x minus a on the bottom as factors. I can cancel. And once I do that, the 0 over 0 problem has gone away. So I've got minus 1 left on the top and x plus 4 times a plus 4 on the bottom. And now I can use direct substitution because the 0 over 0 problem's gone. Okay, and this is just going to be minus 1 over a plus 4 plus a plus 4 is minus 1 over 2 times a plus 4. So we have computed the derivative for that function. Or you want to call a x Any questions?
Where exactly did you get the -1 from again?
Okay, right here.
Yes, ma'am.
You're talking. Yeah. Okay. So what I'm doing, well, what you have basically, sorry, when I I don't really understand why it does it. Okay. So, when I take minus x minus a and I divide it by x minus a, well, x minus a without the minus, it's just, okay, so let me see. Let's see. X minus a over x minus a is just 1, right? So if I have minus x minus a over x minus a, that's -1. Because this minus is really -1 times x minus a. Does that answer your question?
Well, ma'am, I don't exactly get to how exactly we factored the -1 out to initially.
Okay, well, here it is. Let me rewrite this. Okay, so I have, actually, we started with a minus x, right? That was the what we had to start with. And I'm just going to change the form. Well, that's minus x plus a by the commutative properties of numbers. Yeah, I can switch the order. But then, okay, that's minus x minus a, right? And then, okay, well, minus x is really -1 times x. And then this is really -1 times minus a. Or in fact, I could write plus -1 times a. Now I've got -1 times x, and I've got -1 times minus a. Well, I can use the distributive property to factor out the -1. So this is -1 times x plus minus a, right? A times b plus c is ab plus ac. Just using that property. And now I have written it as -1 times x minus a, which is the same thing as just writing minus x minus a. Okay?
Yes, ma'am. Thank you.
You're welcome. Yeah. You can put in all the steps and check that you're using your arithmetic rules to make sure that it holds. Okay. So yes, I can factor out that -1.
I have a question, Ms. Hong, or Dr. Cannon.
Okay.
Around right before you got to the answer, right there, it says -1. We had the limit as x approaches a is -1 over x4 in parentheses, with parentheses right next to it, a plus 4. But then on the next thing, you added a addition sign in the middle.
Good question.
Or why would we do that, or is that just a mistake?
That's wrong. That's what. Okay, that magically appeared. That doesn't belong there, and well, that makes a big difference too. Okay, thank thank you for pointing that out. Okay.
Shout
So
out next one.
it should be this. Yeah, I do make errors, and it really helps if you guys point it out to me. Okay, it should be that. Sorry. Yeah, this just magically changed. That doesn't happen. Okay. So thank you. Well, actually, we are out of time at this point, so we need to end class. Okay, so you may leave unless you want to stick around and ask a question. And I'm gonna go back to my Zoom screen.